Everyone see my screen?
Yes, I can see it.
Awesome. Okay, the agenda for today is we'll go over a searching algorithm, which is commonly used called the binary search, and then some sorting techniques, including selection sort, insertion sort, merge sort, and quick sort. These are primarily used sorting techniques, but there are other ones as well, which we will mention at the end of the presentation. But we'll get started on these.
Maha, your audio got a little bit quiet.
So sorry about that. Is it better
Okay.
now?
Yeah, much better now. Thank you.
Awesome. Okay. So the first one we look at it is binary search. In case of linear search, to search an element in an array, we go over every single index until an element is found. Let's take this example here. If I want to find the element 14, then I have to go from every single element from index 0 to index 1, and from 1 to 2 and 2 to 3. And I keep skipping the element one at a time. Binary search is an algorithm it's used to quicken the search, and this works on a sorted array. When you think about binary search, one analogy is look at a dictionary. Let's say that I want to search a name in a dictionary, and I have a name that I want to search, and I look at the middle page and find that alphabet. Let's say I want to look for R. So I look at the middle element and I compare that element with the alphabet that I have. Let's say I have R. So I compare that M with R, and then I kind of decide where I want to refine my search to. I can either search towards like the right half or the left half. So a binary search is similar to this analogy, where you compare an element with a middle element, kind of refine your search to figure out where you want to narrow down your search to. We'll see this in detail. Before that, I just wanted to point out that the time complexity, the runtime of searching an element using binary search is logarithmic n. So where n is the size of the list. In case of linear search, you have to go like every element at a time. But in case of binary search, every time you're doing the search, you throw away half of the elements. Let's say, let's take our dictionary example, where if you know that if the alphabet that you're looking at is greater than the middle index, all you need to do is search from the middle towards the end. Whereas if it's lesser, let's say I want to search for a name that starts with B, and I don't have to go over the right half of the list from my mid. So all I need to do is check from the start to the mid. Let's see in detail how this works. The algorithm for this particular search is here. So I have an input array, and look for a target element. Just a second, I'm changing this pointer. Okay. So here is the input array, and target is to search for an element 12. So the first step is to calculate the midpoint of this array. So the midpoint lies here at index 3. And now you take two variables which will act as pointer, the start and the end. The start will be the first index of the array, and the end will be the end, the last index of the array. So now, once you calculate the mid, you compare your target with the mid. So here, in this case, the target that I want to search is number 12. Compare that with the mid, which is 14. And you realize that 12 is lesser than 14. So it's it's very important for me to search from the start to the mid, because the element is going to lie somewhere between the start to the mid. So I reduce the mid from, I'm narrowing down my search to find the element from start to mid. So I don't have to look at the right elements or the right hand side of the elements. So this is in case of the target is 12. Let's say the target here is 15, and I do the same thing, take 2 pointers, start and end, calculate the mid, which is index 3 here, and now compare that mid with the target. And in this case, the target is greater than mid. So I have to, there's no point in checking towards the left-hand side of the array. And all I need to do is to search from the mid towards the end. So here, I will move my start to the mid, and my end will remain the same. So now I have a smaller window that I can use to do my search. This is like the um, the 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 primary algorithm that is used for the binary search. We can look at the code. So here's the method, binary search. I don't have the complete code. It's more like a pseudocode. And to find the middle index, you start plus n minus start by 2. That will give like the mid index of the array. And the next step is to have some conditions to kind of check where the target lies when compared with a middle element. So the first condition here is if the item is equal to the middle element that we have calculated. If it's the same, we can right away, we have found the target, so we return that. If it's not, then I just have to adjust my start and end pointers. So if the item is, if the target that I'm looking for is greater than the middle index, then I just have to move the start to mid index plus 1, which is moving my start from 0 to the midpoint. So I don't have to look at the elements in the left hand side. If not, then let's say the item is less than target. Sorry, the target is less than the middle item. So in that case, what we do is move the middle index or move the end pointer to the mid index minus 1. One thing to note here is while calculating the middle element, instead of using if start plus end by 2, if you try to use start plus n minus start by 2, that helps in preventing integer overflow in case of large numbers. The complexity for this time complexity, as we discussed earlier, it's going to be half at every point. Like you're throwing away half elements at each point. So it's logarithmic of n, where n is the number of elements. And best time complexity is O of 1 in case of, if we get lucky, then our mid element could itself be the target. In that case, we just return the element as it is, as defined in this condition here. Any questions so far? Cool. I'll take that as a no. Next part of the session, which is sorting. So this is another example of binary search. Maybe we'll just take a quick look at this one before moving to the sorting algorithms. So here there's an array, and the target that we're supposed to find here is 78. So in order to find 78, the first step that we do is to calculate the mid. And here the mid is 43. So once I calculate the mid, compare that with the target, which is 78. So 43 is less than 78. So my mid is definitely going, my target is definitely going to be somewhere after, after the mid towards the end of the array. So, so I move the start from here to here. So narrow down the search to check for elements only after mid to the end of the array. Here, all we need to do is look at the right half and skip the left half. Now repeat the same thing in the right half of the array. Find the new mid, and here the mid for this right half is 66. Compare, the next step is to compare that with the target. And here the target is 78, the mid is 66, which is the target is greater than our mid. So again, I'll skip the left half and find and just look at the right half of the array. So I move my start pointer from mid plus 1 to mid plus 1, and here the mid plus 1 is 78, and now the start is at 78. And I think here, once you reach this, when you find the mid as 78, then you kind of have the condition to check if your element is greater than, or if it's equal to the mid, then you right away return, you found the target, so you right away return the element as element, which is 78. So you can return either the index or the element. This is a small example that I want to have. I hope this was explanatory. If anyone have any questions, just stop me and feel free to ask any questions.
Yeah, one question I have actually,
Sure.
you explained, start plus, to find out the middle, actually, we need to, somebody asked the question in the chat window, like start plus n minus start by 2, in order to avoid the null pointer exception or integer outbound exception. So could you explain with an example why will it result if you're doing it with the start plus n by 2?
Yeah, I think that's a great question. Let's take like a really great integer, like a really high integer. So in that case, when you calculate the, let's go back to our slide here. And in case, if it's, just assume that this is a very large integer, and integer, there is like a specific limit for the integer, otherwise you will get stack overflow exception in case of large numbers. But if you use, in case of large numbers, if you kind of use this this particular for thing to calculate, like start plus n minus start by 2, that will reduce the size of the integer. You don't have to like add like the really large integers. And when you add really large integers, then it will get to the negative end of the integer and it'll throw an exception. You can just try that using an example. I don't have a compiler right now, but yeah, if you just try with a really large integer using this mid formula, you might get an overflow, integer overflow exception. So that's the reason it's safer to use and in interviews it's safer to use start plus n minus start by 2 in case instead of mid start plus n by 2. This would work for like small integers, but when you get to really large integer, it's safer to use this one instead of start plus n slash 2. Did that answer your question?
Yeah, thank you.
Awesome. Cool. Let's get to the sorting techniques here. And first one we'll look at is insertion sort. So insertion sort works on this concept where you order a list by inserting a particular value into a sorted sublist of the list. What that means is you have a sorted sublist. You keep adding the elements to the sorted sublist in a sorted way. Let's see how that happens. So you consider the first item to be already sorted, and it's of length 1. So this is considered as a sorted sublist of length 1. And now just traverse the array and keep adding elements to this sublist, or you can call this like your cloud. You just have a cloud here, and you just keep adding to this cloud in a sorted way. So here, let's start with the second element. So here 7 is the first element, and you consider 7 to be already sorted, and it's a sorted sublist of length 1. You kind of keep adding to your sublists, elements to your sublist in a sorted way. Let's take the element, the second item here, which is 6. Now you compare the 6 with the 7, and 6 is less than 7. So you perform a swap with 7, and 6 and 7 get swapped here. And just keep doing that for all the elements in the array. So now look at the third element. Now we look at the third element, which is 10 here, and compare that with the previous element, which is 7. So 10 is already at the right place. Compare that with 6. 10 is already at the right place when compared with 6. So just move ahead and look at the next element. Now we take 8 and compare 8 with 10. So 8 is less than 10. So you do a swap, 8 and 10, and then compare 8 with all the elements in the left half, just to make sure that it's in the right order. So in this case here, 8 is greater than 7. So you don't have to worry about it. And you move to the previous position here. 6, compare that with 8, and it's at the, it's at the correct position because 6 is lesser than 8. So we keep doing that until the end of the array, and shift elements as needed. So let's look at the, like the code, and we'll just run over one example. Here is the code for insertion sort. You have a for loop that goes every element in an array, and kind of have that element that you're comparing in a temp variable, and have an variable j that holds the same value as I, and you have a while loop to kind of check if your sublist is having, if the values are lesser, and keep doing that until j reaches 1. So if j is less than 1, or if it's equal to 1, you don't have to look at the first elements, but for all the elements after index 1, we check that if we compare that element with the temp variable, and see if that element is greater, then you kind of add it. Let's go over with an example. I think that will be easier to understand here. So here is a list. We have 4, 1, 3, 2, 5, and you starting at index, I'm skipping index 0 because at index 0 we're not doing anything here. Only if it's greater than 1 it goes into the while loop. So since the first element we already consider that as sorted, we can look at we'll start here from index 1. So you have the I as 1, and temp will be initialized to whatever value I has, and you have j, and j will hold i's value. So here our I is 1. So you have I temp and j as 1 here. And now we'll check in the while loop if j is greater than or equal to 1. Yes, definitely j is greater than 1. It's equal to 1. So here j is 1. So and you also check that if j minus 1 is greater than temp. So j minus 1 here is 4, a of 0. Since j is 1, here 1 minus 1 would be 0. So a of 0 would be 4. And you compare that with temp. So temp is 1 here, 4. So it's greater. 4 is greater than 1. So it's going to go inside the while loop. And what I'm doing, what we're doing here is adding, assigning the value of j minus 1 to j here. And here you have number 4, and you add to j minus, so v of j is 0, and you add 4 to whatever value this j minus 1 has. J minus 1 here is 4. V of j minus 1 is 4 here, and you kind of add, copy that element here to that index 1. And decrement j and go inside the while loop until j is at index 1 or greater, because you want to check all the elements in the left half, like from the start of the list. So in order to do that, you decrement j and keep checking. Here in our case, it's already 1 here, so we don't have to worry about it. And then go to the, so finally there's a last step where you swap that element that you had in temporary variable, which is 1 here, you swap to this position. We don't want to do the swap at the earlier stage, because you just want to make sure that you swap it at the right position. So you keep checking, and once you find the right spot, then you do the swap. Moving to index 2, here i's value would be 2, and so when you swap, the index will become like this value will get swapped. So we get the new array is 4 1 3 2 5. From 4 1 3 2 5 we have 1 4 3 2 5. Now looking at index 2 here, a temp will be 3, and j will hold whatever value I has. And now it does the comparison to check all the elements to the left of I to see if it's lesser or if it's greater in comparison with the temp. Here 3 is definitely smaller than 4. So in that case, we simply do a copy of that element 4 to here. And you don't do the swap yet, like you don't perform this step yet, and then check for all the elements to the left of it. And you compare. Now we have 4. Now 4 is compared with the temp, and sorry, this 1 here, and 1 is compared with the temp. And now it's already at its right position, because 3 is greater than 1, so we don't have to do anything about it. And you exit out of the while loop, and then the final step is to replace j with whatever value temp has. So in this case, temp is 3, and you replace that with v of j. So the array would become 1 3 4 2 5. And we have 2 more elements to look over. And now increment, now you have the outer for loop. So that keeps like checking every element that increments the value of I from 1 to 2, 3, 4. And now I will be 3, and temp will be 2. We are looking at this element right here, and j will hold whatever value I has. So we have j as 3. And now you keep comparing this 2 with all the elements previous to it. So if I compare that with 4 3 1 with the while loop, the first is 4. It's definitely lesser, so it needs to be swapped. Before doing the swap, I just want to make sure that I swap it at the right position. So I keep copying the elements of j minus 1 to j, and now our array would become 1 3 4 4 5. And now j's, we decrement j from 3 to 2, and you check at the element, and if it's greater, 2 is great, 3 is greater than 2, so it needs like it needs that copy as well. So you compare that, and you copy to j minus 1 to j. Here j minus 1 is 3, and you copy that to j. And now we have the element as 1 3 3 4 5. And the while loop will exit, because j value will become 0 after we decrement j. And now you finally perform a swap with whatever value your temp has. Temp is 2, and you swap that with v of j. So j here is 1, so we swap it with j's index. And the last element here is 5, like the last index here is 4 and the element is 5. And now you just keep checking, go through the while loop and check every element. Every time it's greater, so you don't have to do anything about it. It's already at the right position. So the sorting is complete. Any questions so far or comments? Okay, I'll take that as a no, and let's move forward to the next sorting algorithm here.
Hey, Maha, I think there are a few questions in the chat.
Sure, I didn't look at the chat yet. Let me take a look at that.
Yeah,
Okay,
sorry.
here.
So I think one of the questions is about, instead of using another array V, we could do the swap in place in the same array A. Is it possible?
So we are doing this in place. We are not using an additional array here. All we are doing here is having a temporary variable and using that temporary variable to perform our swap. Here, we are not really using another array to do our sorting.
Oh yeah, I think there might just be a typo then, because there's V's in the while loop. We've got, yeah, in the while loop.
So yeah.
Yeah.
I think, yeah, that's I think definitely, sorry. All you do is A, so this and this has to be A. There's no V, or yeah. I think it's just a typo here. Sorry about that. Okay. Sorry about that. It's just one array that we are having, and we're not really having any V here. It's A. This is supposed to be A here. This one is going to be A. Any other questions, Monica? Looking at the chat here. Should I be initialized to 1? Yeah, I think I could be initialized to 1, but when you're using 0, it's going to just skip. It's going to skip 1 iteration if you use 1 here. Yeah, that's a good point. And if you're using 0, it really doesn't go through this while loop, or it just perform this swap with the same element. So yeah, we should be good to use 1 here. Any other questions?
No, I don't see any other questions.
Okay, so let's move over to the next algorithm here, which is selection sort. Just a second. Selection sort is another in-place sorting algorithm. You find the smallest element and swap it with the leftmost unsorted element, and keep doing that for every index. So see here. So here is a detailed description of the selection sort algorithm. So you have 9, 4, 3, 1, 10, and that needs to be sorted in ascending order. So you look at one element at each time and determine which is the lowest element, and you swap it with with our first with the index 0. And here we have a pointer to keep track of the index to go over the array. So let's see. So here, looking at this array, we kind of know that 1 is the smallest, 1 is the lowest. So we swap it at index 0. This is, it's already at index 0. So now we increment the index count from 0 to 1. Now at starting from index 1, you find which is the smallest element. Now you find the smallest element as like looking at these rest of the elements, we know that the smallest element here is 3. Now we have to swap that with index 1. So our index counter is at 1. So you swap that with our with index 1 here. So the array becomes 1, 3, 4, 9, 10. Now you increment the index count from 1 to 2 here. So the element 4, so after 4, we check the smallest element starting from 4. So the 4 is the smallest compared with 9 and 10. So 4 is at the right place, so there's no swap needed. And we move on to the next index. So increment the index count from 2 to 3, and the element here is 9. 9 is the smallest when compared with 9 and 10. There is no smaller elements to perform the swap. 9 is already at the right place. So you just keep incrementing the index count from 3 to 4. And now 10 is already at the right place. So there's no swap needed. So yeah, and the sorting is complete. This is typically how we do the selection sort. And this is, it's slow. And the reason is because every time it has to find, it has to go through the entire list to find the smallest item. So here, this is a really small array, so it's not it's not of a big deal. But let's imagine in case of like a very large array, and for every index, for every index counter, it's going to look for the smallest element. So this selection sort is slow, and the complexity is O of n square, because you kind of have to have like 2 for loops, one to go over the index and the one to find out the smallest element each time. So the worst case is going to be O of n square. Yeah, this is the code for selection sort. You have an outer for loop to go over the elements, and the inner for loop here is to look for the smallest element, the minimum element here. And J starts from I plus 1, because you don't have to look for the elements that you're already visited. So you look for elements after I. So that's the reason we have I plus 1. And here, this code is to find the minimum index. If A of j is less than A of min, then you just swap that index with the min index. So this would give us the minimum index each time. And then finally, here is the step to swap the elements if it's not equal. That's about selection sort. The next Let's look at the next sorting algorithm, which is merge sort. Merge sort is a commonly used algorithm, sorting algorithm. It's also a comparison-based sorting algorithm. You compare the elements, but there are two steps to it. One is to like split the elements into sorted, into smaller lists. Keep doing that until there's only one element in the list. And once you perform the split, when you reach like there's only one element, then kind of uh, merge the same thing, like the steps, the elements that we have split, compare and merge it. And the complexity for merge sort would be n log n in worst and best cases. Let's look into the detail of the merge sort algorithm. Uh, so here there are two steps. One is the split and one is the merge. Here you divide the element into half. So just keep splitting. This is split into two arrays, and this in turn is split into two arrays, and then again it's just split until it reaches an element of size 1. And while doing the merge, compare the elements. 76 is compared with 7, and then a swap is being done. And 86 is compared with 57, and it's not at the right position, so just perform a swap and just keep merging. Now the smaller sublists are compared and added into into the sorted list. So now the next step would be to compare these elements and this 7 and 57, and see that we know that 7 is less. So here we'll have 7, 57, 76 and 86. Let's get into the detail of how we perform this comparison and merging as well in our following slides. So, so the merge sort code is here. Okay, so first step is to split the elements until until the size is just 1. So if it's greater than, if our input arrays size is greater than 2, then we know that we have 2 elements and we have to split that into 1. So we keep splitting that, initialize a new array left, and for elements starting from the index 0 to the mid index, you keep adding that elements to the left. So here in this case, so you find half, and in our left array, we keep adding from index 0 to the half. In the right array, we keep adding the elements from the middle to the end. So that's what our code is here. I0 to mid, which is the half here, and keep adding the elements. Do that for right. Once that is complete, recursively do that for the left half. So now we'll pass this into the function and recursively do that for the left and the right half. Keep doing that until the size is just 1. Once this merge slot is done, sorry about the interruption here. I just have to move to a different location. Awesome. So is my audio better?
Yeah, thank you.
Okay. So yeah, so this step is to split it, and then once it's splitted, then we are going to do the merge step here. So the merge steps takes the left and the right, and it also takes the left the right index, and it also takes that array. Maybe it will be good to have this explained with an example. Let's say we have like the merge. So here in our example, here, let's take this example, go back to our slide and take this example. So you have like the array 76. Let's take an easier one here. This is a small, this is the small, this is an, yeah. Okay, so 776 and 5786. So this is the left and the right. You compare 7 with 57 and know that 7 is lesser. So in our, let me try to draw something here. So compare 7 with 57. You know that 7 is greater. So you have 7 here. And you increment the pointer of this, this array. We have 2 pointers here, and for this one for this array and one for this array. And now since we have added the 7 to the list, we increment from from 0 to 1. And now we have to compare this. Let's say this is I and this is J. I just have it as I here and J here. Now we compare this 76 with 57, and 57 is smaller. So I'm going to add 57 to my result set and increment J. So J would be from 0 to 1. So I would be at 1 and J would also be 1. Now compare I and J. So 76 is less than 86. So I'm just going to add that here. And I ran out of my first list. So the next step is to just add all the elements from my second list. Here it's 86. Yeah. So this is like how do you do the merge? One thing to keep in mind is when you do these comparisons with 2 arrays, all we need to do, we just have to make sure that we don't run out of one array. In that case, we'll have exceptions. So that's why we have this condition here to check if so we have two I1, 2 pointers, I1 and I2. And here you have this condition to make sure that you don't run out of one array. So here we have I1 less than the size of the left array. And here in this case, we have array of length 2. So you do this check only if this condition fulfills. So yeah. Is this like, do you want me to go over like an example with this code, or was it clear? Just let me know in the chat. I haven't looked at the chat yet. Let me take a look at that. Okay. Would the element of the second list sorted? I don't understand the question. Anil, can you brief it?
I think Akanksha Margaret answered it. So I missed the previous step. If the first array we ran out and the second list by I didn't see the previous, in the previous example, I think I missed one row above it. Would this, if there are elements left in the second list when your first list ran out, I was wondering if it would be sorted. But I think this previous row, there is a swap done between 86 and 57 already. So it would, I mean, if there were elements, it would already been sorted by then.
Okay, yeah. Okay, yeah. Let's move. So let's move to the next sort if there are no questions. Next one would be quick sort. Quick sort is faster than the other sorts. So the algorithm for quick sort is to pick a pivot element from the list and order elements so that elements with values less than the pivot comes before the pivot, and elements with values greater than the pivot comes after the pivot. And recursively keep doing that steps with the no the left and the right halves until it reaches 1. Let's see in detail how this algorithm works. And before that, the complexity for quick sort is, in worst case, it's O of n square, and average it's n log n. Let's see in detail how this sort works. So there are two ways where you can do quick sort, and the one that I've explained here is without using an additional space as O of no, just do that in place. How to do the quick sort in place. You pick a pivot element, and here it's 45. I pick the pivot as 45 and traverse the list from the end, that is from the right, until you reach a value that it's greater than the pivot, or that has to be to the right of the pivot. So in quicksort, you have a pivot element and compare the values, and all the elements less than the pivot element no comes before this, and arrange the elements so that all the elements lesser than the pivot comes before it, and all the elements greater comes after it. So here we are traversing the list from the end and the beginning to find that right elements. So when I traverse the list from the right, I keep checking until I find the element that has to be like greater than 45, I mean after 45. So here it's 51 in this case. And then I traverse from the left to see elements that has to be before the pivot, which is lesser than the pivot. So here we found 40, and you just perform the swap. Keep doing that. Let's see how that happens here with an example array. So here is a sample array which has 56, 25, 37, 58, 95, and 19. I pick a pivot here, and pivot is 56. Start traversing from the right towards the left until you find a value that should be to the left of the pivot. So here, so here you have 30. We already found an element that has to be to the left of the pivot, which has to be the left of the 56. So you found that element. The next step is to traverse the list from the beginning until you find the element that should be towards the right of the pivot, should be greater than pivot. So keep checking 25, 37, and you see 58. Now you found that element as 58. Hopefully this. So you found the element which has to be the greater of the pivot, which is 58, and you also found an element that has to be smaller than 56. Now you swap that with each other. So 30 and 58 is being swapped. So the array becomes 56, 25, 37, 30, 95, 19, 73, and 58. Okay, so now we keep doing that again. move from the traverse from the right towards the left until you find a value that has to be to the left of the pivot, or it hits the left marker here, 30. So you check 58, and then 73 is greater than pivot. And then you come to 19, and you know that 19 is less than 56, and it has to be towards the left of 56. So we move our pointer here. Then the next step is to traverse from the left side until we find a value that has to be greater than 56. So you keep checking, and you found 95 here. So 95 have to be after 56, and 19 has to be before 56. Now in that case, but once you find that element, you perform the swap. So 19 is swapped with 95. Now again, we move the we keep doing the same steps that we have done before until the value crosses or it hits the left marker. So here in our case, it has already hit the left marker here from 95. We have come to 19, and when we traverse from here, from left to right, again, it's also 19. So now, so the last step is to compare that with the pivot, and if it's lesser, then perform the swap. So here we have swapped 19 with 56. That's, I think, the sort. So this list is sorted. This is an algorithm for the sort, quick sort. Here's a code. Have a helper function to kind of look for left half and the the right half. So you have the pivot, and you have as the first element, have the left and right index to keep checking from the left and right. And this is to decrement the this while condition is to decrement the count, the counter when if it's greater than the pivot. And you increment the left hand side if it's less than, just to make sure that we find the right elements in comparison with the pivot element. And then finally do the swap. Here, having this to compare the first element, and if it's less than, just swap it with a pivot. Here, that's about quick sort. Yeah, this one I wanted to compare all this sorting techniques, the insertion, selection, merge sort, and quick sort. Insertion, selection, and quick sort, everything is like O of n square in the worst case, and merge sort is n log n, and in the average case is n log n for merge and quick sorts. One of the thing that we should keep in mind while choosing a sorting algorithm is the trade-off between space and time. So merge sort is you keep producing like smaller lists, so it's definitely going to take a lot of space, and you don't want to use it if you're tight on memory. Other sorts that you might want to look at as radix, shell, and heap sorts that we have not discussed, but there are other sorts like bubble sort as well. That's very rarely used. I've just discussed the commonly used sorting techniques here, but it might be worth to just look at the others sorting techniques as well, if you like. And yeah, the last thing I wanted to share is like the variation of the binary search. There are two variations while doing a binary search. There could be like finding a rotation point in sorted array. I think this is one of the commonly asked interview questions. So you have a array that's sorted, but it's rotated, and you have to find the rotation point. So binary search could be used. And in that case, you really don't have a target to compare against. So what we can do is like you can either use, like you can choose like the last element and compare that with the previous elements. Your mid, you can calculate the mid, compare that with the last element, because you don't have like a really target to perform the binary search. So you can choose like a last element of the array to do that comparison against. And the other one, I mean, I can go over the rotation point and sorted array if you prefer doing that. Like we can go over the algorithm. I don't have like a really slide for it, but we can just have an example and talk over it if you want. The second one is like searching an array that contains duplicates. So when we are doing the binary search, let's go back to our binary search piece here. And okay, so here we are assuming that these elements are sorted and they don't have duplicates. Let's say that we have a duplicate element here, like you have 14 here as well. In that case, they might ask you to just return the first occurrence of that target. So, so you just have to add an additional condition in the binary search algorithm. Like here, we can just add an additional condition to check if the element and the previous element are same. Then you just move the mid towards like, you can skip the right half. You move the mid to mid -1. So you can just search from 0 to the mid. And in that case, your mid will be the target and you can return here. In our case, 14, our mid is 14 here. So we'll have an additional logic to check here in this place. In the spot, we can have an additional logic to check if j and j-1 are all same. And if it's the same, then you don't have to do anything here. You can just move your mid to mid -1. So it so this is just considered as another element, and just keep doing the search. That's the variation of binary search. Yeah, I think we are done with the slides. Leave this time open for any questions or discussions. Looking at the chat.
I don't see any questions, Maha. I'll give it another minute. But I just want to say thank you so much. This was a great presentation and really appreciate you putting this together. I know personally, for me, like every time I see I think about quicksort, I really have to think about it. I don't know, it's one that I kind of struggle to wrap my head around, but I really appreciate all the graphics you had. I think those were really helpful. Okay, so there are some questions coming in the chat, so thank you all for asking. So Maha, the first question is, in the pivot sort, when does the pivot switch positions? I believe it's when the elements on when you reach the pivot, either coming in from the left or the right, but can you go back to the pivot?
Yeah, I can go back here. So here in our case, we had when we were coming from the right, we had hit the left marker, and this point we are done with moving, because they have crossed, the left and right pointers have crossed. So that point we have to stop, and the last step is to compare that with the pivot. If it's already smaller than this point, then we are good. We don't need to do any swap. But in case if this element is larger than the pivot, then you swap that with the pivot. Did that answer your question? Shruti?
Yeah, it did. Yeah, thank you.
Sure.
All right, there's one more question. How to determine the midpoint of an even length array? So yeah, if there's 6 elements, should you use, or yeah, 6 elements, what should you use for the midpoint?
We use the same logic here, like start plus end minus start by 2. So let's take an example here. Okay, yeah, this is an element with, this is a list with 6 elements here, and we can just use the same, like start, draw something here, start plus end minus start by 2. So your start will be 0 and end will be 6. So 0 plus 6 by 2 is 3. So you can have this 57 as mid. I think here they had used end. Yeah, here in this particular screenshot, it's it's start plus end by 2. So which is again 3. I wonder how this mid is 2. So okay, I think we are so here, if we just take start and end, our end would be 5 here, 0, 1, 2, 3, 4, 5. There wouldn't be any 6, though there are 6 elements. We have 0 to 5. So yeah, so 2.5, again 2.5 would be rounded off to 2. That's why we have like mid as 2 here, 0, 1, 2. Sorry, I got confused earlier. It's not 6 in this particular case. When you do the start and end, start would be 0 and end would be like 5. So 5 by 2 is 2.5, and here we do like a round off, and it's 2. I don't know if you have a if you have other explanations, Monica, Eileen, for.
Yeah, I think so. Yeah, usually like in math, 0.5 is rounded up, but because we're working with array, if you round up and you're at the end of array for some reason, or max index, you can overstep the bounds of the array. So it's always safer to round down, I think, for that reason. If anyone has other opinions, open to it. Because for a thing like binary search, you'll be searching recursively, right? So start and end might be 0 and 5 at the beginning, but yeah, as the bounds change, it's just always safer to round down. Okay, are there any other questions? I don't see any in the chat. Maybe 0.5 would just be ignored. Yeah, as long as it's consistent here, like in the algorithm, you use the same formula. All right, I am going to stop recording.